Hello, welcome to this video. Today we're going to talk about the volume of an n-dimensional ball. And before we actually jump right into how we actually calculate this, let's first of all show maybe a few examples. So the 0 dimensions is just 1 point, and it's not really a good example, and it seems really a bit tricky to calculate, but one-dimensional is a line. We can do it. And also by volume, I should also mention, I mean the appropriate volume. So one-dimensional volume is length, two-dimensional volume is area, and so on. So if I have, a one-dimensional ball is, well, it's the collection of all the points that are some distance apart, the same distance apart from this point or closer to it. So it's just this line. And if it has radius r, this will be r, this will be r. And the entire length or volume would be 2r. Now for 2 dimensions, we just get a circle. That's about a circle. And as we all know, the area of a circle with radius r is pi r squared. And there are also some cool visualizations for this. It's pretty nice. But then come things like a 3-dimensional ball and its volume. If it has radius r, its volume is suddenly 4 pi r cubed over 3. And if you go on and actually calculate this, well, the one for 4 dimensions would be pi squared r to the 4th over 2. And suddenly the pi is being squared, like something's a bit strange is going on. And so let's do it step by step and actually understand it. So let's say we have our n ball or n-dimensional ball. So we have our ball and we want to understand how to evaluate its volume, say with integrals. So this is what we're gonna do, or at least intuitively this is what we're gonna do. We're gonna chop this up into many different little boxes. So and we're gonna say if we pick some coordinates, say this point is with coordinates x1, x2 up until xn. And let's also name these the directions of the axes. So one axis is x1, another is x2, the other is x3, and so on until xn. And we have n axes. And what we're going to say is, if we have some box at these coordinates, then the length of the part on the x-axis is dx1. So a very small length in the direction of x1. In the direction of x2, we're gonna mark it as dx2, and so on up until dxn. Now on the xn axis, we're gonna mark the tiny length in that direction, dxn. And you might notice I'm here multiplying them, and it's because this represents the volume of our box. Because as you may know, for example, a rectangle, its area is the product of the sides. Some 3D box is the product of its three lengths, and it also works in general. For any n-dimensional box, the volume is just the product of each length in each axis. So now we have this, and we want to sum over all possible x1 up until xn, but we have the constraint that they lie in a sphere. Or in other words, if x1 up until xn is a coordinate inside the sphere, we basically have this constraint. So we need to sum over all values x1 to xn that satisfy this over this. So we basically need to integrate, and we'll have to do n integrals. And here's how we're gonna do this. So we're gonna do it step by step. So we're sort of going to choose, or sort of walk into the place of this box. So we're gonna start in the middle, and then we're gonna walk some x1 in the x1 axis. So we walked some x1, and this is like where we're integrating over dx1. So the outermost integral will be dx1. And what will be its ranges? Well, x1 here can go from negative, here I'm also assuming that the radius of this ball is 1. I didn't mention that, which is a bit important. But say this is an n ball with radius 1. The direction, then x1 can be a minimum of -1 and a maximum of +1. So the outermost integral of dx1 will be from -1 to 1. But then, let's make things a bit more complicated. Let's walk some x2 in the x2 axis. Now what can be the ranges of our x2? Well, we're gonna need to use Pythagoras here, because this is the max. This is, say, the minimum x2 can be, and we know this is 1. We know this is x1. So by Pythagoras, the maximum x2 can be is this is the minimum, so it'll have to be a negative square root 1 minus x1 squared, and the maximum, it'll be a positive. So it's between negative square root 1 minus x1 squared to positive square root 1 minus x1 squared. And let's just continue this example with x3, just so it's clear, just so the case for any n is clear. If we go another x3 in the x3 axis, now x3 can be sort of x3, if we do use Pythagoras again, we'll get that the maximum x3 can be is negative square root 1 minus x1 squared minus x2 squared. So let's understand it in 3 dimensions. It'll be clearer in when we go up to n dimensions. So if this is my starting point, I went x1, went x2, went some x3, and these are all different axes. It's just a bit tough to draw it on a 2D board. But let's say this is the maximum x3 could go, because the minimum is obviously just the minus the maximum. So we know this is basically has to be on the sphere, meaning that this is 1. And we know this is x1 and x2. And so we know this is square root x1 squared plus x2 squared from Pythagoras. And we also know that in 3 dimensions, this line is perpendicular to this line because there are different axes. This is like on the plane of x1, x2, and because x3 is the third axis, it's perpendicular to it, and because this line is on that plane, this line will be perpendicular to this line. Meaning that by Pythagoras, this is y minus x1 squared 1 minus x1 squared minus x2 squared. And this is the maximum, the minimum is just a negative, and you can see how this would generalize into n dimensions. So if you had x1, x2 up until xn minus 1, the maximum xn could go is squared 1 minus x1 squared minus x2 squared all the way on to minus xn minus 1 squared. So now let's do the integral, because we now know the bound of each one of these dx's. So let's mark it like this. The volume of an n-dimensional ball with radius r. Well, first of all, we can say this is r to the n times vn1. So because it's n-dimensional, if we scale r down to 1, then the volume will be scaled by r to the n, meaning that vnr over r to the n is vn1. If we multiply by r to the n, we get this. And now let's do with vn1. We just worked out what the bounds for the integrals are. This is r to the n. And now, first of all, the integral of dx1. It's from -1 to 1. Next is the integral of dx2. It's negative square root 1 minus x1 squared to squared 1 minus x1 squared. And then there's another integral, negative square root 1 minus x1 squared minus x2 squared to the positive of that. And we're gonna have an integrals up until negative square root 1 minus x1 squared minus x2 squared up until minus x and minus 1 squared, and then up until the positive of this square root. And the integral of what this is going to be? Well, this will be the integral of dxn. Then the next will be dxn minus 1. Then dxn minus 2 up until dx1. And you notice I flipped the order here, just so the integrals would be in the right order, but it doesn't matter. So now the order doesn't matter. It just looks a bit cleaner in my opinion. So now we need to actually work this out. So let's look at this integral, because this is just the integral of a constant. This is the integral of 1 dxn. So this is just going to be this minus this. So we're going to have, just because this is something and this is negative something, this minus this will be twice this. So we'll be able to take 2 out, and I'll have 2 r to the n, and then the integral -1 to 1 up until the integral from -1 minus x1 squared up until this time xn minus 2 squared to positive of this. And then we're going to have just this square root. Okay, this is now our current integral. Now this is what I want to do. I want to take the square root 1 minus x1 squared up until minus xn minus 2 squared out of the square root. So it will be square root 1 minus something squared. And I'll have inside the square xn minus 1 divided by the square root. So I'm going to write it just so it's clear. Alright, and this is a square here. You can see this is the same as this, because if I put this into this square root, everything will just cancel out and we'll end up with this. But notice this square root 1 minus x1 squared up until xn minus 2 squared is a constant in our xn minus 1 world. And so we can use here a simple u substitution. So let's do u is equal to xn minus 1 divided by square root 1 minus x1 squared minus until xn minus 2 squared. And so du will be the same thing. It will be dxn minus 1 divided by this. So dxn minus 1 is du times this. So we'll have actually du times this square root and this square root. So this will turn out to be just squared, and the square will cancel out. Here we'll have just 1 minus u squared, and the bounds will change from just negative 1 to 1. So this is twice to the n, integral from negative 1 to 1, and the next integral, this time of u, will just be the integral from negative 1 to 1. And now here, like I said, dxn minus 1 is u times this square root. This and this is the same, so will just be squared. The squared and the square root will cancel out, and we'll get just this. And all of this is multiplied by square root 1 minus u squared. Then this is du dxn minus 2 until dx1. Now, let's see. So this, like we said, is a constant in the xn minus 1 world, and so it's a constant also in the u world. So we'll be able to take it out of the u integral, and we'll be left with the integral from negative 1 to 1 of square root 1 minus u squared. So let's think about what is the integral from negative 1 to 1 of square root 1 minus u squared du. So let's think about the definition of let's think of the definition of this integral with bounds. So if we have, let's say this is u, this is v, and we have the function v is equal to square root 1 minus u squared, the integral from negative 1 to 1 will be just the area from negative 1 to 1. But notice, if we rearrange a bit, we'll end up u squared plus v squared is equal to 1. So this is a circle. But it's not a circle exactly, it's actually a semicircle, because when we did the square root, v could also be the negative of square root 1 minus u squared. And by taking the positive, we basically said v is positive, so we're taking the top part of the circle, and so we get a semicircle from negative 1 to 1. So this is just the area of a semicircle, and this is radius 1. So this is just pi over 2. So this integral will be pi over 2 times this. And then we'll be able to take the pi over 2 out. Pi over 2 times 2 will be just pi. And we will end up with pi r to the n, the integral from negative 1 to 1, until the integral negative square root 1 minus x1 squared minus x minus 3 squared square root 1 minus x1 squared minus xn minus 3 squared. And now we have this integral. This is the integral minus x1 squared minus x2 squared minus xn minus 2 squared. And then dxn minus 2, dxn minus 3, and so on until dx1. This is our new integral. And now notice that we can actually split these apart. So we'll have pi r to the n, then all these integrals of just 1, dxn minus 2, dxn minus 3, until dx1. And then this is going to be minus all these pi r to the n, all these integrals of x1 squared plus x2 squared plus up until xn minus 2 squared, and then dxn minus 2 up until dx1. So let's write this, but before I write it, actually, let's remember the first part of that will be, let's ignore these constants for now. We'll have the integral from -1 to 1 up until the integral from this of just dxn minus 2, dxn minus 3 up until dx1. This times r to the n minus times, well, this is exactly just vn minus 2 of 1. Look at this. This is the same, but except 1, but if we write instead of 1, instead of n minus 2, we'll have the exact first part of that sum. And so, what we'll actually have is the first bit will be pi r to the n vn minus 2, 1. And then this is going to be minus a bit of a minus an annoying integral. And then we'll have x1 squared plus x2 squared up until xn minus 2 squared, dxn minus 2 until dx1. So we can actually get a recursion formula out of this if we just work out what this is in terms of some vn's. So let's think about the geometric meaning of this. What does this integral actually mean? Well, it means that if we have our n ball, what we're doing is, this is actually an n minus 2 ball, but dimensional ball, if we're basically saying look at any point and then evaluate the radius squared. So basically not the radius but the distance from the origin squared, because because it's x1 squared up until xn minus 2 squared. That's exactly the distance from the origin squared. We're saying evaluate that and then average over all points. But what we can cleverly say is, let's, instead of doing it for every point inside the sphere, let's instead do sort of like surfaces of the sphere inside. So we'll have one with this radius, then another with this radius, and we'll have one integral across the radius of r squared times the surface area of each one of these sort of closing spheres. So we're cutting it, so again, to reiterate, we're cutting it into spheres, into many different spheres, and then to average over the radius squared, we'll do the integral of r squared, but then we'll also have to account how many times to how many points are on that sphere of radius r. So we'll have to multiply by the surface area of an n minus 2 dimensional sphere with radius r. So let's move it to the other side of the. So let's move it to the other side of the board, and we'll continue to evaluate this. So this is what we got up to, and I already replaced our integral with this. And again, we're calculating the average of the radius squared. So we're taking each sphere of radius r, and r is going from 0 to 1. Taking the radius squared times the amount of points on times the amount of points on that sphere, which is Sn minus 2r dr. So this is the integral, and Sn minus 2 of r is the surface area. And we actually want to find a correlation between Sn minus 2 and Vn, or Vn minus 2, something that'll help us to use this reduction formula. Well, it turns out the derivative of Sn of r, the derivative of Vnr with respect to r is Snr. So let's show this. So let's say you have an n ball with radius r and another n ball with radius r plus dr. And let's think of the volume of this shape. On the one hand, it's just the volume of an n ball with radius r plus dr minus the volume of an n ball with radius r. But on the other hand, it is approximately just if we're saying dr is very small, the surface area in this shape, the surface area on the inside is about the same on the outside, and so it'll be about just dr times this surface area. So dr times Snr. And in fact, as dr goes to 0, this will turn to an exact equals, and so when dividing by dr, we'll end up that this is dVnr, which is this small difference in Vn, divided by dr, which is exactly the derivative. The derivative of Vnr with respect to r is Snr. So now let's use this here. We're going to do integration by parts. Let's pick u to be r squared. dv is Sn minus 2r dr. And I'm picking it like so because I do want to integrate Sn minus 2r to get Vn minus 2r, so I can get a reduction formula with just Vn's, no Sn's. So this means V will be, like we just proved, Vnr, and du will be 2r dr. So this is now pi r to the n Vn minus 2, 1 minus so pi r to the n time, so this integral will be, this is the integral u dv by integration by parts. It is equal to uv minus the integral of v du. In this case, u times v is r squared Vn minus 2 of r. R goes from 0 to 1. So let's write this. This is pi. So this is a minus, so it will be minus, in our case, uv. So because we have this minus in the beginning, so times r squared Vn minus 2r, and r goes from 0 to 1. And then plus, because at first it was a negative, but this minus turned into a plus, we have now the integral from 0 to 1 of v du. So of course, pi to the r to the n in the beginning, and 2r vn minus 2r dr. But now let's look at what this is. This thing alone is, well, at r equals 1, this is vn minus 2 of 1. At r equals 0, this is just 0. So this thing is equal to pi r to the n vn minus 2 1. But notice, this is the same as this. So, this cancels out. And, well, let's take the 2 out of this integral. This is 2 pi r to the n. It's the integral from 0 to 1 of r vn minus 2r dr. Now we did reduce our integral, but it seems like we need to reduce it again and to know what the integral of vn minus 2r is in order to do that. But actually, we can use something very clever. So we can say vnr, we said in the beginning it's vn1 times r to the n. But this is just a constant. The only thing that can change this value is n. So this is a constant in terms of n. This is the n times r to the n. And so we can actually plug it into here. So we'll be able to get a reduction formula for Cn. And when we find Cn, we'll just multiply by r to the n to get v and r. So let's do this. We'll have Cn r to the n is equal to 2 pi r to the n, and the integral from 0 to 1 of r times Cn minus 2 r to the n minus 2 dr. Now, first of all, I'm going to cancel r to the n, and we'll have Cn is equal to, I'm going to take Cn minus 2 out of the integral, and this is going to be the integral from 0 to 1 of r to the n minus 1 dr. This is just r to the n over n. From 0 to 1, this will be 1 over n. So in total, this is 2 pi Cn minus 2 over n. Now we have a reduction formula for Cn, and now we can find it. So first of all, we need 2 starting points to get all, Cn for all n. So we need C1. C1 is just the length, well, it's the volume of a one-dimensional sphere of one-dimensional ball with radius 1. But like we said at the beginning, this is just a line, where this is the center, this is 1, and this is 1. So this is 2 in total. And C2, this is going to be a circle, about a circle with radius 1, and its area is going to be pi. So we have these 2 initial values. Now we can tackle Cn. So let's do it for evens and odds. So C2n, what is it going to be? Well, like in our formula, this is 2 pi over 2n, C2n minus 2. 2 cancels out, this is pi over n. And this is equal to, we use a reduction formula. You get pi over n times, a 2 will cancel again, we'll have pi over n minus 1. And pi over n minus 2 up until we'll have pi over pi over 2 times c2. Now notice we're multiplying with this is a product of n minus 1 terms. So this is just going to be in the top. Pi to the n minus 1. And then c2 is pi, so we'll multiply it by pi. In the bottom we have n times n minus 1 times n minus 2 up until 2. This is exactly n factorial. So this is pi to the n over n factorial. Now, c2n plus 1. This will be a bit uglier, but at the end it'll actually turn out really nice. So let's do this. We're going to have 2 pi over 2n plus 1 times c2n minus 1. And again, this is going to be 2 pi times 2 pi. Again, this time we will have n products divided. So then to n minus 1, and then up until 3. And then this is times c1. So at the top we will have, let's do this like this. This is going to be pi to the n. And then we will have n plus, so we will have, these are n2s, and at the bottom we have n terms. Let's bring these 2's down. So we'll have 2n plus 1 over 2 times 2n minus 1 over 2, all the way out to times 3 over 2. And now, this is times c1, which is 2. And I'll write 2 as 1 over a half. So this will be multiplied by a half. Now, this seems very close to this sort of divide by 2 in factorial. Because here we divided this by 2 and did a factorial. This seems very close to dividing this by 2 and doing a factorial. Because if we get this somehow to be 1/2 factorial, after multiplying by 3/2, it will be 3 over 2 factorial, then 5 over 2 factorial, and so on, and we will have 2n plus 1 over 2 factorial. And in order to make it 1/2 factorial, so what the question is really, what do we need to multiply by to make this a 1/2 factorial? The answer is square root pi. So 1/2 factorial is famously square root pi over 2. So if we multiply and divide by square root pi, we will get this. Now this is 1/2 factorial. Since 3 over 2 is 3 over 2 factorial, then 5 over 2 factorial, up until 2n plus 1 over 2 factorial. And notice at the top, square root pi is pi to the 1/2. So we'll have pi to the power of n plus a half. And I'm sure as all of you know, n plus a half, or 0.5, is just 2n plus 1 over 2. So all in all, this is pi to the 2n plus 1 over 2 divided by 2n plus 1 over 2 factorial. Really, I should write this with the gamma function, as the factorial is defined by only 2 natural numbers, and the gamma function is what extend this to the all real numbers. So I will write this as pi to the 2n plus 1 over 2 divided by gamma of 2n plus 1 over 2 plus 1, because the gamma function is shifted by 1. So we need to add a plus 1 to make it 2n plus 1 over 2 factorial. So this is actually the same as this. Because this can actually be written as pi to the 2n over 2 divided by 2n over 2 factorial, and gamma of natural numbers is actually factorial. So end up with this. And so in general, for all natural numbers, Cn is pi to the n over 2 divided by gamma of n over 2 plus 1, meaning that the volume of an n-dimensional ball with radius r is just r to the n times Cn, which is pi to the n over 2 divided by gamma n over 2 plus 1 times r to the n. And you can really check and find that for 1, it spits out 2, or that, let's ignore the coefficients r to the n. If you look at Cn, for 1 it spits out 2, for 2 it spits out pi, for 3 it spits out 4 pi over 3, for 4 it spits out pi squared over 2, and so on. So this is like a sort of check that this is really the formula, and the checks worked, so we can be pretty sure that we're right, and we are. This is the formula. And finally, that's it. If you want more content like this, please subscribe to my channel. I'm uploading more interesting problems and things like this in the future. And finally, that's it.